So we are going to look at a characterization of compactness of a topological space. We are going to look at that characterization, the characterization of compactness of a topological space. I think we discussed about the characterization of compactness in a subspace topology. Now this is characterization of compactness of a topological space. The other one was characterization of compactness in subspace topology. So what does the theorem state? Let X be, this is a theorem, let X be a topological space. Let X be a topological space. So we are going to say that X is compact. X is compact if and only if X is compact if and only if for every collection, if and only if for every collection, which I'm calling that symbol, if and only if for every collection that, if and only if for every collection this of closed sets in X, that have the finite intersection property. X is compact if and only if for every collection that of closed sets in X that have the finite intersection property would have this intersection of elements, intersection of elements which we are actually picking from this collection. This collection is non-empty. So that is an important theorem. So we are saying that X is a topological space. X is compact if and only if for every collection, so it's compact if and only if for every collection of closed sets in X, every collection of closed sets in X that have the finite intersection property, we have this intersection as a non-empty set. So what we are saying is that those closed sets with the F.I.P property, try to get their intersection. The intersection should have something. So how can we encounter this? It's an if and only if statement. So suppose that X is compact. Suppose that X is compact for every collection, and let this be a collection. It's a collection of closed sets in X with the F.I.P property. Now we are going to prove this by contradiction. Suppose by way of contradiction that actually this set here, suppose that this set is empty. Suppose that set is empty. So what does that mean? This means that then we all know that X can be written in form of X minus the empty set. This is equal to X minus the empty set now, which is the intersection which is this intersection. Now what we can actually do, what this is the same as the intersection of x minus c. We can bring that there by the distributive law of that intersection. We can bring this here. So what do we have? X now is equal to this intersection. X is now equal to this intersection. X is equal to this intersection. Actually, I think there is something which I have to deal with. This is x minus the intersection. So by De Morgan's law, if I'm to bring this in here by De Morgan's law, this will actually become the union. This is simply the union by De Morgan's law. Yeah. So that's what I am having. So what is this informing me? So we are having x as a union of these elements. So hope you remember the definition of an open cover. So it's like we are saying now x can be expressed as a union of these elements. So that implies that these elements now they are forming an open cover of x. So observe that this collection now, is an open cover of x. Is an open cover of x, and we know that x is compact. It's an open cover of x, and we know that x is compact. So there exists a finite subcover, an open cover of x, and since x is compact, comma, x has a finite subcover from this set. X has a finite subcover from that set. So let this be gamma equaling to x minus c1, x minus c2, up to x minus ck, up to x minus ck. What next now? That is a finite subcover of x. Now we can actually write x as then x is simply the union from I equals 1 up to k x minus ci. So this is equal to we are going to try to put x outside by De Morgan's law. If I want to put that x outside, so this is x minus the intersection from I equals 1 up to k ci. So what does this inform us? So this is actually telling us that if x is equal to this, now, if this side is equal to this side, then this should be an empty set, then the intersection from I equals 1 up to k ci is equal to an empty set. This is a contradiction. This symbol means contradiction. This is a contradiction. Why is it a contradiction? We suppose that this is a collection of closed sets in X. It's a collection of closed sets in X with a finite intersection property. By the previous definition, we define what it means for this collection to be having a finite intersection property. This intersection here, the intersection of a finite subcollection of elements from that set shouldn't actually be an empty set. So this contradicts it's a contradiction to the F.I.P property. So implying that our original assumption was wrong. So this implies that the intersection of C E. I see this is equal to, this is not actually an empty set. It's not actually an empty set. So what have we done here? We have been able to suppose by contradiction and the set is empty, then x can be written as x minus the empty set. X minus the empty set. I think that is the complement of the empty set. The complement of the empty set. So x is equal to x minus the empty set. Then we can substitute this here. Then by De Morgan's law, if I want to bring this inside, I will make it the union. Now observe that these C's, the C, these are closed sets. These are closed sets. They are closed sets. Now their complement here, their complement forms open sets. So these are open sets. We're having a union of open sets. So that union forms an open cover of X, because X is now being expressed as a union of these elements. So suddenly they form an open cover of X. Since X is compact, we have this finite subcover. Then we can represent this in that form. Then we shall conclude that the intersection is actually an empty set. So we are going to look at the other side. So conversely, suppose that every collection of closed sets, every collection of this of closed sets in X having the F.I.P property. Suppose that we have this having a F.I.P property. Suppose that we have this. Now we show that X is actually compact. So we supposed to show that X is actually compact. So still the proof is going to follow by contradiction. So by contradiction, we are going to suppose that X is not compact. So if X is not compact, by definition of a compact space, we say that a space is compact if every open cover has a finite subcover. So we are saying that X is not compact. That means there exists an open cover without a finite subcover. So then this implies that there exists an open cover of X. There exists an open cover of X without a finite subcover of X. So there exists an open cover of X without a finite subcover of X. So let this be, let me call it this symbol W. So there exists an open cover of X, which I'm calling W, without a finite subcover. So what does that mean? That implies that W has no finite subcover. W has no finite subcover of X. W has no finite, it has no finite subcover of X. It has no finite subcover of X. So what does that imply? That implies that X, this implies that X cannot be expressed as a union. X cannot be expressed as a union, cannot be expressed as a finite union, I from 1 up to K, finite union of WI's, finite union of WI's, yes. If W has no finite subcover of X, so X cannot be expressed as a union of WI's, whereby these WI's are coming from W. So this implies that if X is not actually equal to that union, then X minus I from 1 up to K WI, this is not an empty set. This is not an empty set. So by De Morgan's law, we can try to bring this X inside. So we shall have the intersection from I equals 1 up to K X minus WI. By De Morgan's law, we shall change this from union to intersection. This is not an empty set. So we suppose that every collection of closed sets, observe that these W are open sets, since they form an open cover. So this is a collection of open sets. These are open sets, and hence their complement is closed. So this is the intersection of closed sets. So what did we say? We say that every collection of closed sets. So we are having this collection of closed sets with the finite intersection property. Now this is a non-empty set. So this collection has the finite intersection property. Come again. Suppose that every collection of closed sets in X having the finite intersection property. So this is a collection which is having a finite intersection property, and this collection, the collection X minus W, a collection X minus W, should I call it WI? This collection here, let me call it just the collection. The collection of sets of this nature. This collection here, the collection of sets of this nature. The collection of sets of this nature is consisting of closed sets. Consisting of closed sets, and they have the finite intersection property. So by hypothesis, if they have the finite intersection property, then this intersection should be non-empty. Collection of any collection is consisting of closed sets with the finite intersection property, and by hypothesis, by our hypothesis, we have the intersection WI from W X minus WI. This is a non-empty set. The non-empty set. Allow me call this WI, whereby WI is from W. This is a non-empty set, and by the Morgan's law, this implies that we can actually express this as X minus the union WI this is not an empty set. So that means X is not equal to the union WI, whereby WI is coming from W. So X cannot be expressed as a union, of sets WI which are picked from W. X is not equal to the union of elements which are in W. So that means W, so this implies that W is not an open cover of X. Not an open cover of X. This is a contradiction, because we suppose that W is an open cover of X without a finite subcover. So we are being able to show that W is not actually covered by X. So W is not an open cover of X, and this is a contradiction to our original assumption, implying that X is